Thank you very much. And yeah, so this belongs to model theory. The question is that instead of having a single model of some theory, we want to look at some continuously parameterized family of models. And I didn't give any references in this slide, but this has some history, but very sporadic history. So for example, in the, I don't know, 80s, 70s, Angus MacIntyre used these parameterized families to prove that a certain theory has a model companion, which means that the existentially closed models can be axiomatized. So use these abstract model theory to something very concrete that is very classically model theory. And then, for example, Andrés Villaveses and his group in Bogota, they also study these models living over topological spaces. But it's a bit sporadic. So I want to start with what is a continuous family of models. And for that, how to make that precise, that you have a family of models which changes continuously over some space. And so for that, I have to say what is a sheaf, let's say a sheaf of structures. So here's an example that you have some topological space, and for every open set in this space, you send that to the set of continuous functions from that open to the real line. And now if you have some smaller open, then you can restrict, so you get a map in the opposite direction, which means that you have some contravariant functor from the lattice of opens to the category of sets. So that is called a pre-sheaf. This is why these very simple things, just functor categories from some category to sets, which is a very simple object, has such a fancy name. It's coming from this. That's why they are called pre-sheaf categories. And now this example has some additional property, which says that if you have some covering of this open set U, then to give a continuous function on this big open is the same as giving continuous functions on the small opens which coincide on the intersections. Okay, so that's the gluing axiom or the sheaf axiom. Now, instead of just a sheaf of sets, we want a sheaf of L structures. Okay, so for each open, we send it not just to a set, but to some L structure, where L is some signature. So for example, in this example, this is a sheaf of L ring structures. Well, it's even a sheaf of commutative rings with the pointwise operations. Okay, so you can think of this continuous functions from U to the real line as a commutative ring with pointwise addition and multiplication. Good. So that was a sheaf of structures, but in model theory we are interested in a sheaf of models or continuous family of models. So what is that? It's a bit more complicated, but not much more complicated. A bit more complicated than a sheaf of models. Okay, maybe the title is not good. Okay, so you do not send every open to some model. So what is a stalk? If you have this topological space and you have a point in that, then so this still belongs to my previous example of continuous functions. Okay, you look at the continuous function germs. So functions which are defined on some neighborhood of that point up to having the same refinement to some smaller neighborhood. Okay, and this set of these equivalence classes, the set of these function germs, that's the stalk in this particular sheaf. Yes, and in general, it's defined with this colimit formula. Okay, so you take the colimit of the values of this sheaf or pre-sheaf along the neighborhood basis of that point. And now the definition is that a sheaf of L structures is a model if each stalk is a model. Okay, so you have these operations that you have in the L structure, they can be restricted or they are meaningful on these equivalence classes. You can just apply them to the representatives, and then you have an L structure in each stalk, and you want that L structure is a model. So a very classical example is that if T is the theory of commutative local rings, which means that everything that is, that means that if the sum of two invertible things is, the sum of two non-invertible things is again non-invertible. So this is such a thing. Okay, so this continuous functions to the real line that is a locally ringed space, because each of these stalks are local rings, because being non-invertible means that in X your function germ is 0. Yes, so your function germ is 0 in X, and that is clearly preserved for addition. So now the question is there some model theory of sheaves? Okay, so if you know some model theory of local rings, can you get some results for locally ringed spaces? Okay? Can you generalize from just models living over a point to models living over topological spaces? And for that, there is some technical tool, some very elegant version of algebraic logic, which is called categorical logic. And the idea is that we want theories to be mathematical objects. I mean, that was the original reason for introducing algebraic logic. People realized that the Lindenbaum-Tarski algebras are very important, and in zero-order logic, you would always identify zero-order theories with Boolean algebras, or in the negation-free fragment with distributive lattices. And so then Tarski had the idea that let's do the same with first-order theories, and that led to cylindric algebras, which are some handmade gluing of these Lindenbaum-Tarski algebras. And there is a very simple and maybe more canonical way to do that. And so this is a bit too many symbols, but it's very simple. Okay, so you have some theory, say you have some complete theory, okay? And then you just look at the category of zero definable sets. So zero definable means definable without parameters. Okay, you look at the category of zero definable sets, which means those sets which can be cut out by a formula. And the morphisms are the definable functions, those functions whose graph can be cut out by a formula. Okay, so, and the idea is that you can replace your theory with this category of zero definable sets. So that's not an arbitrary category, because these zero definable sets, they are closed under some operations. Okay, so if you have two definable sets, then their product will be a definable set. You can find a formula which defines that, and so on. And so these are called coherent categories, which have finite limits, pullback stable finite unions, and pullback stable image factorizations. And you can identify theories with those things. And then models will be the same as set-valued coherent functors, so just functors which preserve these finite limits, finite unions, and effective epimorphisms. And the homomorphisms will be the same as natural transformations. So there's a dictionary between classical model theory and category theory. And you could even generalize that, or it also makes sense for internal models. So models internally to some category are just the same as E-valued coherent functors. So in particular, if I'm interested in these continuous families of models, then in fact I'm interested in coherent functors from this category of zero definable sets to sheaves on my topological space. And now you can ask, is there, for example, a compactness theorem? And the answer is, it depends on what you mean by the compactness theorem. Okay, so if you mean that every finitely consistent theory has a model, then the answer is that's trivial. Yes, because if it's consistent, then it has a set model, and then you can just take the constant family of that set model. So that's not interesting. But there are some other versions which do depend on this parametrization of the models. Okay, so and one will be ultra products, the other one will be realizing types. So this is an ultra product. You have a set, and over each point there is there's an index set, and in each index there is a set, and you consider choice functions up to the equivalence that they coincide on some ultra big set. Okay, so that's the ultra product. But you could also phrase it category theoretically. So this is just, you take these products of these structures, but not all of them, just ultra many of them, and then you take these refinements, yeah? So these colimit along the projections, then you get the same thing. So now you can ask, is it true that if you have some collection of X parametrized families of models, then that ultra product will be an X parametrized family of models? Or alternatively, you can ask that, is it true that coherent functors from some small coherent category to sheaves on X is closed under ultra products in this full functor category? Okay. And the answer is no. And this is one example. So here, maybe I don't have time to explain the examples, but so here the idea is that some distributivity property fails. Okay, so in the category of sets, infinite intersections interact well, distribute with infinite unions. But in sheaves over topological spaces, only finite intersections interact well with infinite unions, and the ultra product construction can see that, and for that reason it can fail. Another example is that the motto for the other example is that if you have these continuous families of models, then maybe you can take their ultra product, but the result will be a continuous family of models living over a bigger space. So yeah, because you could also, yes, you should also, so for example, if your models are living over the spectrum of a Boolean algebra, then the ultra product will live on the spectrum of the ultra product of the Boolean algebras. Okay, so that's another reason why it fails. Good. So another instance that we can talk and which doesn't fail is realizing types. So this is the idea. You have this lattice of closed formulas, let's say closed positive existential formulas, and you have a lattice homomorphism from this to the lattice of opens. And you think of it as you prescribe that I want that phi is true on this open and psi is true in this other open, phi and psi is true on the intersection, and so on. Okay? And now you ask, can I find a parametrized family of models such that these stalks, yes, they satisfy all the prescribed formulas? Now this has some elegant category theoretic formulation as a lifting property, yes, so that these subobjects of one, that's the lattice of closed formulas when you think about this category of definable sets, and a homomorphism like that is just a coherent functor like that, and this property is expressed by this triangle having this natural transformation in it. Okay, so the claim is that if X is an extremally disconnected stone space, so it is the spectrum of a complete Boolean algebra, then the answer is yes. So you have this. You can prescribe formulas on open sets, and you can find a model which satisfies that. So the idea for that, so first, the idea is that, so the first idea is that you can reduce the situation to the situation when your complete Boolean algebra is a power set Boolean algebra. And that's because every complete Boolean algebra is a retract of a power set Boolean algebra, because complete Boolean algebras are injective objects in the category of Boolean algebras or distributive lattices. And now the idea is that this is how the spectrum of a power set Boolean algebra looks like. Yeah? So it's the space of ultrafilters. You have the isolated points, which are the principal ultrafilters, and your basic opens or basic clopens are given by subsets of your index set, and here you have all the ultrafilters which contain that set. So now the idea is that at some principal ultrafilter you find your favorite model which satisfies all the prescribed formulas there. You can do that because that's classical. And now your parametrized family will do this, yes, that at some point which is not a principal ultrafilter, your given model will be just the ultra product corresponding to that point of your family. Okay, so you have to do some work to make this precise, but it can be made precise. And now, sorry. And now you can also generalize it a bit. So this was complete Boolean algebras. And a bit more general is that if L is a distributive lattice and Q is a well-founded forest, and L is a retract of the lattice of upsets, then also this spectrum of L can realize types. And you might say that these are very special topological spaces. Who cares about spectrums of distributive lattices? But if you could do it for spectrums of complete distributive lattices, then you could do it for any topological space by a very easy argument. And so now I have two questions which would make this, this step possible, yes, to get from these very special, or not that special spectral spaces to all spectral spaces. So the two questions, first one is a model theory question. Assume that you have some poset, okay, and you have a theory, and K is this lattice of closed formulas, closed positive existential formulas. Now the difference between just considering positive existential formulas or considering all formulas is that ultrafilters cannot contain each other, but prime filters can. Okay, so now assume that you have a poset, and on each vertex of this poset, you have a prime filter. Okay, so some type, some positive type, and whenever some vertex is bigger, your type is extended. Now the question, can you find a Q-index family of models and homomorphisms such that each model models the type that was prescribed there? Okay? So can you do that? If this is a well-founded forest, then you can do it very easily. You just do this in the bottom, and then inductively you do it. But for general posets, I don't know. And a question about lattices, maybe this is well-known, I don't know, that assume that you have some distributive lattice, yes? Then there's its canonical extension is this embedding, that you embed it to the lattice of upsets of the spectrum. Okay, so prime filters with the embedding as ordering. So it sends some element to those primes which contain that element. Now, the question is, if I have some complete distributive lattice, is it true, or when is it true that this embedding splits? Okay, so that I also have a homomorphism from this upset lattice to L, and the composition is identity. Now, if B is a complete Boolean algebra, then it splits because B is an injective object. And if L is completely distributive, then it also splits because there is some result that this canonical extension happens to be the free completely distributive lattice over L. Okay, so if you know the answer to either the model theory or the lattice theory question, then let me know. Okay, so thank you.